can you share screen or something, or just
yeah.
share?
Can you see my screen?
Yep.
Okay. So I'm an assistant psychology at Peking University, and I do computational modeling, but I also use behavioral and neural imaging experiment to explore human cognition and decision making.
Cool.
What I'm really interested recently is to reinterpret classical psychological and behavioral phenomena from a decision theoretic approach. That means everything is decision making. So some keywords about my research: Bayesian decision theory, uncertainty, probability, distortion, perception, action, attention, decision making, and bounded rationality. That's me. Thanks.
Excellent. Okay.
So I can stop. Close. How can I close that?
Yeah, you can close that. And Wei, why don't you start by introducing yourself?
Okay. I am Kunlin Wei, and I'm also in the same department as Zhang. I'm also in psychological and cognitive sciences at Peking University. I'm a motor control guy, basically study how people control their movements. And also the related question will be how to learn to control their movements. My research tools, I'm doing a lot of behavior studies. Then because once you have the behavior data, you need to have some modeling of that so you can explain the things better. Recently, I'm working on how the virtual reality change people's perception or action control. I'm also working on, because we got so much data, so I have to do some brain imaging now. So that's my new frontiers for me.
Great. Well, let's get started. We're waiting for Alex to reconnect, our third guest today. But we already have a starting question.
Yep.
So what is the difference between bias and variance when we're fitting models or thinking about models? What's the bias variance trade-off?
Maybe Han first.
Well, I'm not sure about the terminology. So could Zara or Zahra, could you clarify your question? Like, so did you mean
I can
two specific terms?
I can give a try. I mean, maybe what he's asking is in terms of the accuracy and the precision. Accurate means whether we can, if I can make an analogy, is if you throw a dot, whether you can hit the bull's eye. That's about accuracy. The precision is about the variance. Is if I throw the dots 100 times, how variable I am. So that's precision. Accuracy versus precision is very relevant statistic question. But for the bias and the variance, you can think about this way. In model fitting, the bias is if you fit a model, whether the model fitting, whether the model prediction actually match the data very well. If there is some systematic deviations, that's what we call bias. And if you if the model is overfitting the data, then your model prediction will be very variable. That's we mentioned today in day 3. We call it variance, bias and variance trade-off. I hope I answered your question. But these two are very related concepts. If I put it another way, whether your model has large bias or not, or it is basically answer the question whether your model is valid, whether it can explain the data, whether your model is accurate in terms of capturing what's going on in the data. Then variance is another thing. It's just like a precision. Is how variable your model prediction will be. So if you overfitting the data, your model prediction will go all over the place. Your model will capture some unwanted noise in the data, which is not the real thing, but that will make your model prediction more variable. I hope I answered your question well.
And actually, could I add something? I don't think we use like accuracy versus precision in the context of model fitting very often. It's not looks familiar to me. I agree with Kunlin that it's a statistical term that when you quantify the prediction, like how useful is your prediction or how good is your prediction, you can use accuracy versus precision. But I can't see why we should like connect these two, bias versus variance.
Well, maybe at a general level, one thing that's connected is the idea of whether we do cross-validation or not, right? So in sort of simple statistics, we have this concept of a bias-variance trade-off, but when we're fitting models, one thing we have to deal with is that it's very easy to overfit on a specific data set, right? We get lower variance in the sense that we get a improved model prediction, but we do it at the expense of being biased towards the particular data set we're looking at. So when we do cross-validation, we actually, we may have a model that has more uncertainty, or we may have less well-estimated parameters, but we know that we're less biased in the sense that we're predicting out of sample. So there's one way that they can be thought of as related.
Yeah, I agree.
So, yeah, go on.
So are we taking a different question or?
Yeah, we're going to take a different question. So let's take a look here and see. So let's talk about this idea of estimating a model and what is cross-validation. How do we start with that? So does one of you want to give us a description of cross-validation?
Which question it is? I mean, I'm looking at the questions and answers, and what was the specific question that put on a question board?
Yeah. So the specific question is, in cross-validation, what is the intuition behind validating or using residuals from held-out data?
Are we looking at the same list?
Yes, I can see. The question is, in cross-validation, what is the intuition behind the validating using residuals from held-out data?
So the question, I think, is when you're looking at the held out data to determine the error of your model, right? Let's say you fit a model and you ask, what's the residuals or what's the unexplained information in my test data? We know that that's biased. But if we use the residuals or unexplained information in the out of sample data, then that gives us information about whether we're getting better or worse in the out of sample data, right?
Mm-hmm. Yeah, I want to add on is when you do model fitting, and it's like you are doing the model fitting. Sometimes you will pick the best features. You will pick the best model that can explain your data. So you're bringing a lot of subjective biases to get out of the training data. But if you have some held out data, so you can calculate it as residuals, this part of the error captures both of your prediction error, which means how generable your model is, because by training data you already get your own model, right? You get your model parameters, but by using the test data set, you can test how the generalization of your model, which is very important. So the residual error of test data set not only included the generalization error, also including its own, I would say, the training error, because in this sense, it not only making new predictions, also has it reflects the original variance the model can captures. So the test set actually is very important. It's as I said, the first reason is reduce the influence of subjective biases. this is very important for us for doing models. Did I give it my
I think
idea?
that's a, yeah, I think.
Oh,
In fact, cross validation is like a golden standard for testing your model. Nowadays, if you just provide your training data, you're saying I have a high R square, it won't tell people, it won't convince people that your model is good. It's always using a test data set. You hold up the data set to test whether your model is good, whether it can provide good performance. Because at the end of the day, the reason for us to build a model is to predict, right? To predict the things on things instead of just explain the existing data set.
Yeah, so one thing that I like to say is that if you just want to actually describe your data, for example, let's say you're using a linear model and you want to ask, I want to know the relationship between two things, but I just want to think of it as a description, then cross-validation may not be as important because what you're trying to do is get the best description. But mostly in neuroscience, when we're making a model, we want a model that we think is actually modeling some process that's really going on, that's actually something that's general. And so when we do cross-validation, we're trying to make something that's closer to what we think is a generative model or a true model. And there, you really want that model to be predicting the data that you haven't yet seen because you assume the process is general. You're not just trying to describe your data set. You're actually trying to model a process that was going on that produced the data set. So I think that's a nice conceptual difference. So let's see if we can pick another question.
shall we pick from the top of the list that has the highest vote?
Sure, let's see. Well, I think we've started answering sort of this mean squared error on the training set question, right? Well, there's a question here that's a bit broad about different kinds of models. I don't know, do you want to ask about the possible kinds of models like Bayesian models or reinforcement learning models?
Oh, which one? Which question?
Which question?
If anyone could talk about the different applications of reinforcement learning or Bayesian inference, what are the advantages of them? It's a question from Jovan Ho.
Could you put your mouse on it so we can see a red square around it?
It's a last question. Actually, where is it?
Where is it?
I can see.
I think I can click on it.
You see it now?
Yeah, it's highlighted. Difference,
okay.
Difference application.
So let's see if our video is back. And wait, we have Alex here, I think. Hi, Alex, can you hear me?
I'm back too.
Yeah, no, I wanted to see if we could.
Looks I'm here too.
Ah.
No. Sorry, I have a lot of trouble connecting. I'm really sorry about this. I'm actually in France. Yeah, and I have poor connection. That must be why. And we've lost Zhang. No.
Oh.
Yeah. Okay.
Yeah, so Alex, you just want to introduce yourself for 30 seconds?
Yeah, Kunlin, I've missed some part of it, so I let you decide which question to go next. Probably. Oh, okay, I can do that. So hi everyone. Very sorry for not being here from the beginning. Let's hope I will stay there until the end. I'm Alexander Hyafil. I'm based in Barcelona, did my PhD in France, where I'm from, and I'm mostly interested in perception mechanisms, doing computation modeling of perception. Previously, I used to work a lot on oscillations and neural dynamics, underlying perception. But now I'm mostly working on Bayesian models of perception and trying to understand exactly how those models can work, not just in the kind of very simplistic environments where usually we put subjects in experiment, but also in more richer experiments where there's a lot of information to integrate, and like the structure of environment gets so difficult that you cannot do that the Bayesian solution to perception is no longer feasible for the brain, is not tractable. So yeah, these are things that you've heard about a bit during the outro with Kunlin, and you'll see more things on Bayesian stuff in future days. And basically, this is it. Yeah, I'm doing mostly modeling, but also analysis of data sets that are acquired from experimental colleagues. And I think everyone is back except Jeff, no?
Yeah. Jeff's not in today, but he's helping run things behind the scenes. So we have another question here. Maybe Alex, you want to add a little thoughts there. There's a question again about what variance means when we're doing model fitting on different test data across different data sets. Well, we've lost Alex again.
No. I think when you have that. Oh yeah. Sorry.
That sounds reasonably clear to me. Let's hope it's done answering their question. Yes, go on.
Oh, I just have one comment that whether a model, a expected model, is overfitting, or it depends on the richness of the data set. So if there are two models, one A is more complex than B, then for like when you have very few data sets, you may find like model A is just overfitting. But if you have a model data set, maybe model A is not overfitting. It's the appropriate level. So it has something to do with the data set, not only just, not absolute thing. Yeah, don't know.
Yeah, I mean, I think one of the problems we always have in neuroscience, right, is we don't actually know what the true model is. And I wanted to bring up something we haven't discussed yet, and I haven't seen a question on it, but maybe you can think about it a little bit for a few minutes. When we write down a model and we think it's describing, let's say, how neural activity works, or say control and motor behavior, if we get the model wrong, then we're going to see something that looks like variance or noise, right? We're going to not be able to explain something, but in some sense, it might be a model that's okay, and the data might be very clean, but it's actually not the right model, right? So we're having trouble explaining things in a very consistent way. So here, to use linear models as an example that's quite easy to understand, if you fit a linear model and you go and you look at the residuals, or what's left over, and you see that there's a lot of structure in the residuals, right? They don't look like noise, but they look like there's actually blobs that are clustered together, or there's some kind of other structure in it. You can think to yourself, oh, my model is just actually the wrong model, and the reason I'm seeing this variance here is not because of noise in the data, or noise in the fitting, but it's actually that we need to adjust our model. So how do you think about that? Might need to, you need to reload.
Yeah. But if
so, yeah, what do you think about this? So how do you think about knowing whether you're seeing problems in your fitting, you're seeing errors? How do you decide whether you need to change the model, or whether you think it's in the data, that you need to collect more data, or the data is just noisy? How do you think about that?
Well, I know all the models are wrong.
Yeah.
So
also.
yeah, it depends on whether I have opportunity to collect more data. So at every moment, your research has some kind of constraint. So either you can't collect more data, or you don't have more time to do more explorations on the models. So the truth, we can't get the truth, never. It's just we are approaching it.
Well,
I'm
a very optimistic guy, so I guess that's a very good question. So sometimes you get residuals. Residual is right there. How can I know residual is true noise, or is some kind of, you still have some, or because your model is not good enough to capture it? I guess when you learn, how can I say, traditional statistics, when we need to check those residuals by our eyes, which means sometimes if you plot those residuals, you think if it is noise has no structure. Noise has no structure. For example, if the noise distribution is flat, or it is Gaussian as you assumed, then you have a larger confidence. You have more confidence in saying it's true noise. But if the residual, or the model fitting residual, if you plot against X, you have a multiple X or multiple Y. If you're plotting against some X, you find some structure in it. For example, the noise amplitude, the residual amplitude, dependent on your magnitude of the X, then you know there is something going on in the data which is not captured by your model. Then you need to improve your model. So the way we handle noise versus true noise versus some pattern, we need to check your residuals, sometimes by eyeballing the data, sometimes by building multiple models. So if you can't just have one model, right? You need to think more as many models as you can, so you can spread out the spectrum. You can try all kinds of things. Then you can compare model. You can see whether the residual can be reduced. So the way I handle this question is to make sure is true noise is, first, I try multiple models. Second, I check those residuals. I'm trying to find any structure in the residual. If there is any, then I need to rethink about my model.
So there's go ahead.
Sorry. Okay, I just want to ask a question. So when will you choose to stop? How good is good enough? When will you choose stop testing more new models? How good is good enough?
Well, that's covered in day 1 and day 2. I guess is the whole philosophy of a model fitting. Sometimes you based on your theory, sometimes based on new data, sometimes based on your intuition. Sometimes you need to combine all these, right? Model is, as I said, all models are wrong, but we're making incremental progress towards more truth, right? So it's just a gradual process. Sometimes you need to be satisfied with yourself, with your progress.
Yeah. So go on.
Sorry, this time this time you first.
No, so I was going to say, I think one thing that we haven't talked about here at all, and I don't see a question about it yet, but it's often the case that the right way to think about it is just as Wei was saying, that you're actually doing model comparison, right? We know there's another model, and I could add another model, and I could add another model, and I can always ask, is this model better or worse? Am I doing better with respect to the number of parameters of the model that I have? So if we have 2 parameters and I describe the data well, and I add 20 more parameters and I gain a small amount, we don't think that that's actually useful normally, because we always apply a penalty for these over-parameterized models. We sort of have the sense of Occam's razor, trying to keep it as simple as possible. But at the end of the day, we're always comparing models. My null model is, a constant. Stuff happens and everything is noise, and then I work up from there. But you're always having to ask yourself, is this model good enough to give you an intuition for the question you're trying to answer? And I think that often comes to the question you're trying to answer. So, if you want to make a very detailed prediction about some small aspect of behavior of the brain, you're going to need a more complicated model, but it probably will do less well describing, a different brain area or a slight variation on the behavior.
Yep.
If what you want to do is write down a more principled open model that captures a lot of behavior or a bunch of details of brain activity, then you're going to have to trade off a little bit in specificity to keep the model tractable given the amount of data you have. So you're always making choices, scientific choices, right? We have to think about what's the purpose of this model. There's no perfect right answer. Is that fair?
Yeah, I agree.
Okay. Yeah.
So,
I think we are very typical neuroscientists, and for computer scientists, the answer may be different, because they are more interested in the accuracy of prediction, not about understanding the mechanisms of the brain. So we are basically use our model to test hypotheses, not just to say this model is best.
Mm-hmm.
So there's another question here asking about why do we do cross-validation rather than just doing something like R squared? What the general error is of the model. So we have a couple of questions here also about the difference between bootstrapping and forms of cross-validation. So the general question first, how do you decide what measures to use? So we know when we're doing model comparison, we can use things like the Bayesian information criteria, for example. So how does one know what the right approach is to assessing the model? When is, say, just looking at the R squared an acceptable approach? When should you cross-validate? When should you use bootstrapping? what's the reason for choosing one of these measures?
Mm-hmm.
I think here are some. Sorry, I think here is a combination of some simple and some more advanced questions. For the basic question, should I use R-squared? Of course, you should compensate for the number of parameters in your model. You can use R-squared with cross-validation. So you can cross-validate your R-squared. That's okay. But you can't compare models with like one model has 2 parameters, the other has 20 parameters, and then you compare their R-squared. That's unfair. That's just unfair.
Yeah.
Because
So when you this is for me. So if you just describe your own model, just one model, or multiple models, and you need to in your description you have to report R-squared. But whenever, just as Zhang said, whenever you're trying to compare model, then R-squared is not enough. And furthermore, there were many places, if you have multiple models have different complexities. So R-squared is truly not enough. So you need to consider to punish your model complexity. In the tutorial, we say the cross-validation is great because, as I said, the cross-validation, in fact, is testing how generalizable your model is, which is great. Mm-hmm. We also have some alternatives. I guess, I don't know whether it's covered in tutorial. We have AIC, BIC, we have all kinds of measures to compare models, which also has the spirit of cross-validation because it punishes model complexity. So as I said, if in my research, if I have several models, if they share the same complexity, then I'm fine with R-squareds, right? But if they have a different complexity or they even have a different spirit, they have a different structure, they are just fundamentally different models. Sometimes I really want to know which model is best. So the R-squared is way not enough. Just don't even consider. So cross-validation, because cross-validation can test the model on new data set, which is great. Okay, so cross-validation or AIC, BIC, these things will convince people that the one model will be the best model. Okay.
Yeah. So here's there's another question that's related, which I wanted to bring up. Is it worth just plotting the results of your model against the data visually? Is that a good way to evaluate the model? What could you learn from that? I mean, one of the problems when we look at the end result of a model fit is obviously we have a single number like our negative log likelihood or our BIC. But that doesn't necessarily give us much intuition about how the model is working or how the model is failing. So, plotting the simulated results of the model might be actually helpful. What do you think?
I can make an analog, like say the AIC or BIC or any kind of index of goodness fit is like a GDP of a country. And all kinds of the behaviors of models, like look at how people in a country, how they live, what's their life look like.
Okay.
So it's one is some index, so you can compare across different models, and the other is the real life of model. Is if you want to understand a model, like to understand your pet, or to understand another person, then you should observe the model and observe its behavior.
Yeah. So let me answer the target question. It's saying plotting the simulation result and realizing one figure is give a visual impression. It's always necessary to have some scientific way to evaluate your goodness of model. I guess plotting the data with your model prediction, of course, is important. I mean, this is the way. Actually, we do this all the time during model building, right? We need to plot the data, but not always. Sometimes your model prediction and the data could be have a lot of dimensions. Sometimes it is very hard to visualize it. So that's why we need to invent those, say, tests or condensed variables like AIC, BIC, those kind of things to look at the model quality. Eyeballing is great. and we use it all the time, but not always. Sometimes it becomes very difficult. This is just my experience. Yeah.
Yeah, because humans are very good pattern recognizers. Like you can recognize patterns that are still difficult for machines to learn. So eyeballing the data can give you some insight. Say, when you develop a new model, usually you start from what's the feature of the data, as well as the previous series.
So let's see. There's another question here that I think is important to ask, which is, we've been talking about, how to fit a model, how to compare models using all of these formal criteria. But what about biological plausibility? So how do you think about whether your model is actually one that makes sense as a biological model? And do you make that decision? Do you say this is an abstract model that doesn't have to be biologically plausible? Or do you include biological plausibility as your as one of your criteria, which you can't easily turn into a number necessarily?
Actually, not for me, because I work on the computational theory level, so it's very far from implementation. I understand that, like, different levels, they are actually constraining each other, but in reality, it's very far. Like, say, the same computational theory level models, they can be implemented in very many different ways that we can't imagine nowadays, maybe. So, but for people who are interested how like a neural circuit works, then it's very important for you to understand the biological constraint, because that's probably your contribution is. So I think it's like different people, different modelers are working on different levels. It's hard to say, I want to build a model that has all biologically plausible, and I also show it can produce very complicated human behavior. I think that's the ideal, but we're still far from that.
Well, I think this is a great question. I mean, this is why C asked whether we should care about biological plausibility. I guess we need to consider, in terms of cognitive science, we are doing research on 3 levels. In terms of David Moss said 3 levels, right? One is computation level, the other algorithmic level, the other one is implementational. When you talk about the biological plausibility, I think maybe is the 3rd level, is the implementational level. If you build a model for that level, of course you need to ask about biological plausibility. But if you asking some high-level question, like why the human brain need to save energy, why we care about to use our brain less. This is actually one of the highest priority of our brain, is to use the brain less, making less effort, mental effort. And if you're asking this kind of question, then you build a model on a computational level, which is very different. And sometimes you can't even think about any linkage between this kind of model and a biological plausibility, right? So it really depends on what kind of questioning you ask and what kind of level your questioning is. We don't always trying to find the biological plausibility for a model. That's what I'm saying.
I think there is an analog, like you can say, should I learn how the computer hardware works before I learn any programming, or before I learn any to program an artificial intelligence like agent? So do I need to learn all the ways computer works or my operating system works? Not necessarily.
Yeah, I guess, it's one of those questions that may depend on exactly what you're doing. So we have a technical question here, which I guess relates to when we're doing cross-validation. Often we do k-fold cross-validation, right? There's leave one out cross-validation where we take all of the data and we leave only one sample out and we predict it. But normally that's very expensive. So we do, some number. So the question is, how do you select the K for your k-fold cross-validation? How do you know what the right split should be and whether you've done it enough to do efficient cross-validation?
Yeah. Han, do you have any opinions on this? How do you choose?
Could you repeat the question? I can't see the question.
Let me ask you. So, how do you pick the K for k-fold cross-validation? Which K do you pick? What's your?
Oh, actually, if K is so, if K is the number of data set, then you have the leave one out algorithm. And actually, like AIC is kind of an asymptote of the leave one out cross validation. So at the very end, you are approaching some say AIC, and at the very end, the other end, actually it comes back to the bias versus variance, the bias variance trade-off question. So when you have less number of folds, you will have more variance but less bias. Sorry, I think when you have more, is it reverse? Is if you have a big fold, then yes, exactly. Yeah, because the larger your training set, is more like you have a less to test. So your bias will be reduced, but your variance will be increased. So twofold cross-validation would give you the highest variance. The highest variance, but less bias. Mm-hmm. And which one to choose, it depends on the purpose and the status of your data set. So we once had a data set that's not very informative, and we found that when we are doing, say, 10-fold cross-validation, then it's very strange. We got cross-validation. So if we have a permutation test, so we generate a data set with no information, then we found when we do such a cross-validation, then we get some kind of negative correlation. And then we did some research. Actually, what I found is that there are not very many literature on this issue, although it's a very practical issue in many different data analysis procedures, like very often used in analyzing neuroimaging data. So there are a few paper on it. What we found is some neuroimaging, some paper on neuroimage, the journal. They talk about it.
Yeah, exactly. So there is no best answer for this. It depends on what kind of research question you are, what kind of area you are in. For example, in neurophysiology data, a lot of people using 10-fold. They recommend it, but in some research area, they don't use 10-fold. For example, if you're trying to train your model and using model to predict whether some people get COVID-19, so leave one out will maybe your best cross-validation, because you need to predict one individual, right? So leave one out is exactly for these purposes. Also, it depends on, depends on what kind of question you ask and what area are you in. The third factor you need to consider is how much data you have. How much data you have. As I put in the outro, as I said, the cross-validation really need a lot of data. And if you have a few data, sometimes you can't even do good cross-validation. So if you have a lot of data, you can do more generous cross-validation, cut the data less.
So Alex, now that you're back, I don't know whether you can hear us and we can hear you. I wanted to know if you had any comments on any of the questions that we've been answering or anything you wanted to add. I saw that you mentioned that we should only use models that are actually scientifically and sensible. Is that the right way to say it?
Yeah, I've tried to type in a number of answers, but usually the moment I was finished typing, you already guys had said it. So yeah, and I think what I was trying to write was basically what Kunlin was explaining. Yeah, so we're talking about biological plausibility. And yeah, I guess it depends whether you should, how to weigh in biological plausibility depends on what's your research interest, in which level you want to be. But it needs to be, you only need to test good models in the sense that models that make sense for you, that are plausible candidates for the phenomenon you want to describe, whether it's at a very detailed biological level or at a very abstract level. So I mean, to me, this should be the first filter of
We're losing you.
Well, we had it.
We're just trying to get the most out of him.
Have that for a moment. All right. So wait, why don't we take a few minutes, because somebody asked if you could talk a little bit more about your VR experiments. So maybe you can spend just a minute doing that as we're closing things out.
Oh, okay, great. I using the VR. One thing is I give people the hand that doesn't have, so they have a virtual hand, right? Then when they using the virtual hand to do a lot of stuff in virtual reality, they think the hand is their own hand, and they're using psychological method to prove that. So when the avatar hand is making some movement out of their intention, or not related to their intention, they feel like the avatar hand is moved by themselves. I use some measure. Recently, because the VR has this kind of power, I'm trying to show whether this kind of embodiment can be measured in the brain. Because VR can change people's embodiment. I already have some behavior data. Now, recently, I'm planning some fMRI study on this. Then the other thing I did is, in the reality, our world is the object appear larger when it's nearby, and it is smaller when it's far. I can reverse this relationship in virtual reality, right? That's a weird word, because the object will appear smaller when it's closer. When it's far away, it's getting bigger. So I manipulate this kind of a visual perspective in virtual reality, and then I change people's visual perception already. And the next step, of course, is doing fMRI, and then we can study how the object size and distance relate, how is it represented in the brain. And the other VR application is, phantom limb patients, phantom limb pain, which means if you are amputee, you have at least 50% have this kind of pain for your missing arm. Then in the virtual reality, I give them the arm back. So they can control a virtual hand, a virtual arm in the virtual space. That reduces the pain dramatically. And recently, the paper is accepted. And the next step is we can, of course, to test how that change their brain representation in their brain. Because the arm is missing, but the representation is there. Why it causes so much pain, and why VR can actually alleviate the pain. So there is some cool stuff happening in virtual realities.
Well, that's very cool. I actually know somebody in a lab here who's been doing some similar work, and I think it's a lot of fun. I did one of these experiments where I had to move my hand around, and they were playing with whether the hand was moving in the virtual reality the way I was moving it. You know, I was reaching and grabbing things, and it felt a little cool and a little eerie trying to decide whether the hand was really doing what I was expecting or not.
I like the wording, eerie. It is eerie sometimes.
So, Hung, I was wondering whether you could answer the question, what advice would you give for a young scientist? Is there anything you wish you would have done differently?
Well, it's a big question.
So maybe just, is there some advice that you would give scientists when they think about doing modeling in their careers? You know, what's the big picture perspective? Something that you feel people should think about when they're starting out and beginning this process?
I think it's good to start with some big questions, like a big picture about the brain. So I talked about you don't need to know all the biological constraints, but I think I should take something back that actually we need to look at how the brain works. Even it's not every detail, but you should have a big picture. Like say, know some neurobiology, and you know some psychology. And it's very important to connect to human behavior, and also to how the brain works, how the different brain regions, they coordinate. I think for us, it's very easy to lose the big picture when you like dive into your own question. But just something's there, and from time to time, there may be some new trends that people suddenly find, there's some new theory. It's very useful to apply to neuroscience. I don't mean like we need to always like catch, this is a hot spot, so I want to work on it. But I still appreciate the new ideas underlying the trend. Like that's something probably help us to make breakthroughs. But at the same time, I pretty enjoy working on my own small area, and I hope could make it more popular in the future.
Well, we should wrap up for today, but I want to thank Wei and Kunlin and Zhang and Alex Hyafil, who is unfortunately only transiently with us. We've been actually doing, you don't know this, but we've been doing a random bootstrapping test where we sample the number of participants who are going to be on screen at one time, and Alex kept being left out of the fold. So hopefully we will see you tomorrow morning, and hopefully we'll have a few less technical problems. A reminder, please fill in your daily student reflections and enjoy the rest of your day. See you tomorrow.
See ya. Thank you, guys. Keep asking good questions, okay? I love your questions.